All right, let's walk through this problem here with a pumpkin astronaut. Just Halloween, so this is appropriate. The pumpkin astronaut is orbiting a newly discovered Earth-like planet. The pumpkin orbits with a period of 12 hours at a distance of 50,000. 50,000 uh, meters above the surface of the Earth. No, 50,000, 500,000 meters, 500,000 meters above the Earth's surface. And the radius of this planet is 3.5 times 10 to the 6 meters. Okay, so all physics problem. You draw a picture. Here is the planet. We know the radius of this planet. R. R equals 3.5 times 10 to the 6th meters. And the pumpkin is out here. The astronaut is out here. Some distance, 5 times 10 to the 5th meters above. All right, so the pumpkin is orbiting like so. That's not even close to round, but that's okay. There's our pumpkin. Astronaut going around like so. The pumpkin has a mass 500 kilograms. Determine the speed of the pumpkin. Speed, velocity, is distance divided by time. Well, the distance this thing is going to go, right? He goes one complete revolution. One complete revolution would be the circumference of that circle. Circumference is 2 pi r divided by time. But the r is not really the radius of the planet or how far above. It's the both. This r here, the radius of the orbit is going to be the radius of the planet plus the altitude of the pumpkin. So the radius here, 2 pi, and this is going to be 3.5 times 10 to the 6th meters plus 5 times 10 to the 5th meters over the period in which it completes this path. It completes this path, one full circle, in 12 hours. So let's figure out a couple of things here. Let's do some math. 3.5 second E6 plus 5 second E5. That's 2 pi 4 times 10 to the 6th meters over 12 hours. 2 pi times second answer is 2.513 yada 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 513 times 10 to the 7th meters in 12 hours. Now, hours is not really the opportune thing. We always want to go to meters per second. So how many seconds are in 12 hours, right? 12 hours, do a little bit of a unit conversion. There in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. So you have to take our 12, multiply it by 3,600. 4 times 60 times 60. And we come up with 43. What do here? 43,200 seconds. So we get 2.513 times 10 to the 7th meters divided by 43,200 seconds. $582, call it, meters per second. That's the speed. Determine the mass of the planet. Okay. Now, the mass of the planet, this guy's going in a circle. Remember, F equals ma. This guy's going in a circle. So this becomes centripetal acceleration. F equals mv squared over r. Now, this is the centripetal force. The centripetal force is the gravitational attraction. What keeps this pumpkin astronaut in orbit is the gravitational attraction. So really, the force of gravity equals mv squared over r. This would be the mass of the pumpkin astronaut. Well, the force of gravity is the universal gravitational constant times the mass of the planet times the mass of the pumpkin astronaut divided by the separation between them squared. That equals the mass of the pumpkin astronaut, the velocity of the pumpkin astronaut squared divided by the separation between them. This is kind of nice. A couple of things cancel out here. Okay, that's not so easy to recognize, but hopefully you can recognize it. Mass of the pumpkin astronaut, mass of the pumpkin astronaut, those go away. This R cancels out one of those R's. So we end up with the universal gravitational constant multiplied by the mass of the planet equals, this is divided by R also, separation equals V squared. We want to solve that. We know that we just solved for the velocity, the guy there. That's a constant, and that was 4 times 10 to the 6th. So we know everything but the mass of the planet. We can solve this. The mass of the planet is going to be equal to V squared times R divided by the universal gravitational constant. Rearranging this equation, inverting and multiply, right? Take the G and the R, bring it to the other side of the equation. If you take the G and the R and bring it to the other side of the equation, invert and multiply. So you go there. That's your new equation. And you come up with 582 meters per second squared multiplied by 4 times 10 to the 6th meters divided by G, 6.67, thank you, Mr. Henry Cavendish, times 10 to the negative newtons per meters squared per kilograms squared. And all of that equals, what does that equal? 582 squared times 4 times 10 to the 6th. And that's going to, the numerator becomes 1.35489, yada, 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 times 10 to the 12th seconds divided by the universal gravitational constant, 6.67 times 10 to the minus 11, newtons meters squared per kilogram squared. And we get the mass of the planet equal to pretty much 2.03 times 10 to the 22nd kilograms. In terms of units, how does that work out by units? Remember, a newton is a kilogram times a meter per second squared. So our seconds up here, we end up with, this is a second squared, right? Meters squared per second squared. So this is meters per second squared. We end up this one. Meters per second squared cancels out meters per second squared. Kilogram cancels out one of those kilograms. So we're going to end up with a kilogram and a newton. All the units cancel out. Meters per second squared is the A and A. Yeah. So we just end up with kilograms. And that is the answer for the mass of the planet. 2.03 times 10 to the 22nd. 2.03 times 10 to the 22nd kilograms. Determine the acceleration due to gravity on this planet. The acceleration due to gravity. Remember this equation. Force of gravity equals G m planet m object over r squared. The acceleration due to gravity is just this. Right? On Earth, all of that equals 9.81. But on this planet, it would be 6.67 times 10 to the minus 11th newtons, meters squared per kilogram squared, times the mass of the planet, 2.03 times 10 to the 22nd kilograms, divided by the separation, the radius of the planet. The radius of the planet, just the planet, 3.5 times 10 to the 6. 3.5 times 10 to the 6th meters squared. You do this arithmetic, 6.67, second E negative 11 times 2.03, second E 22 equals that, divided by 3.5, second E 6 squared. All of that, oh my goodness, it's like nothing. 0.11 meters per second squared. Ha. This thing doesn't weigh. This planet is not very exciting. Well, yep, double check the math. That's the number. That's tiny. Okay, so that's ridiculous. On Earth, it gets 9.8. So 0.11. Ha. And what would the astronaut weigh on the surface of this planet? At least 500 kilograms. So his weight would be all of that times 500 kilograms, or 0.11 meters per second squared times 500 kilograms. That would be the G for that planet, and that would be the M, mass of the day. So 500 we get 55 newtons. Whoa, 55 newtons. What would he weigh? 55 newtons. That is the problem.